The third coordinate system we will use in this course is the spherical coordinate system with the variables r, theta, and phi. I want to mention something that you'll have to get used to that is different than what you were taught in your math courses. Mathematicians in the U.S. switched the roles of the second and third variables from virtually all other scientists and engineers, as well as mathematicians in other countries. So this will prove to be some confusion early on that you have to get used to. The variable r can take on values from 0 to infinity, the angle variable theta from angles of 0 to pi radians, and the angle variable phi from angles of 0 to 2 pi radians. The variable r defines a spherical surface whose center is at the origin and r is the radius of the sphere. R equals 5 meters would define some spherical surface like this sphere shown here of radius 5 meters. The variable theta defines the surface of a cone whose apex is at the origin and the angle from the z-axis to the cone's surface is theta. If theta were equal to pi over 3, then this is the conical surface that would be defined. The intersection of our sphere and our cone will result in a circle, shown right here. The third variable phi is the same as the one we work with in cylindrical coordinate system. It's an infinite half plane. One end is tied to the z-axis, and the angle phi is the angle the plane makes with the x-axis. If phi is equal to, say, pi over 4, it would define this plane right here, and we see that it intersects our circle at one point, the point P here. So the point P is the intersection of three surfaces, a sphere, a cone, and a plane. Right at our point, the three surfaces are all orthogonal. Here is the conical surface defined by theta. If theta goes to 0, so as this angle gets smaller, we see that this cone will collapse and eventually just be the positive z-axis. So when you say theta is equal to 0, it defines the positive z-axis. If theta is equal to pi over 2, then this cone keeps widening until it's essentially flat and becomes the xy plane. So theta equals to pi over 2 defines the xy plane. Now let's let theta keep increasing beyond pi over 2, and it's going to become a cone again, but now with the part of the cone below the xy plane. So here's a cone for a theta angle greater than pi over 2, and you can see as theta approaches pi radians, the cone will collapse and be the negative z-axis. So here is a theta equal to pi radians, and so the cone has collapsed to be the negative z-axis. Let's now look at the unit vectors in the spherical coordinate system. So the unit vectors point in the direction of increasing component value. If r gets larger, this sphere will be expanding, so the direction of increase is this arrow right here. So that's the unit vector in the r direction. If theta is increasing, then this cone will get broader and broader, so at point P, the direction of increasing theta would be in the direction of the arrow shown here. So that's our unit vector in the theta direction. Theta getting larger means this plane would sweep in the direction of this arrow here. So this is our unit vector in the phi direction. At point P, these three unit vectors are all orthogonal. So the unit vector in the r direction crossed with the unit vector in the theta direction will give us the unit vector in the phi direction. We can represent a vector at a point in space as components in the Cartesian coordinate system, or its components in the cylindrical coordinate system, or its components in the spherical coordinate system. If we're given the vector represented as components in the Cartesian coordinate system, let's look to see how we would find the components in the spherical coordinate system. Here we have the same vector represented either as components in the Cartesian coordinate system or as components in the spherical coordinate system. If we take this representation and dot both sides by the unit vector in the r direction, on the left-hand side we'll have our vector dotted with our unit vector in the r direction. On the right-hand side, a sub r dot a sub r is 1, so that will just leave the component in the r direction. A sub r dot a theta is 0, and a sub r dot a phi is 0. Now we'll take the vector with the components in the Cartesian coordinate system and dot it with the unit vector in the r direction. So the left-hand side will just be the component in the r direction, so clearly the right-hand side also has to be the component in the r direction. So taking this dot product here and distributing it, we get this result. So by finding these dot products between these unit vectors, we can convert from the representation in Cartesian coordinates to find the component in the r direction in spherical coordinates. Similarly, by taking the dot product of our vectors with the unit vector in the theta direction, we can get the theta component, and by taking the dot product with the unit vector in the phi direction, we can get the phi component. It's harder to evaluate these dot products than it was in the cylindrical coordinate system, so I'm not going to go over that. In fact, I've never gone to the trouble of verifying it, but here's a table from your textbook that shows the results of those dot products. So for instance, the unit vector in the y direction dotted with the unit vector in the theta direction is cosine theta times sine of phi.